Okay. Okay, so I mentioned that I haven't brought the card reader, so please sign the sheets, just so I can get the attendance. Now, first of all, before I start the lecture, when are you going away for your field trip?
Next week.
Next week?
Yes.
Okay. So you want a lecture next Thursday, do you?
Yes.
Okay, that's good. So what I'll do, by next Thursday, we will finish all of the course material, but there will be plenty of problems. I've sent through some problems to you. I uploaded them to Blackboard last week. There's some problems at the end of this lecture slide, and there'll be some problems at the end of the next lecture slide for you to practice. Now, what I'll do is after Easter, we will have 2 more lecture slots. I won't give any more material, but there'll be opportunities in those 2 lecture slots to either have 2 hours of drop-in, so that you can come in to my office or I'll arrange a place, or we can have the 2-hour slots in here. So I don't know what you'd prefer, for me to go through the examples and work them on the board with you, or whether you'd prefer to have drop-in. Does anybody have a preference? Does anyone prefer how they'd like to go through the worked examples? But I think that what you want to do, or what you should do, is go through the examples and find out where there are problems, or that there are things that you don't understand before, so that will be after Easter, before those slots. And then let me know whether you want to have drop-in sessions or whether you want to do them in the lecture period. Okay, so I'll wait for that feedback from you. Now, I don't want to go over too much of a recap from what we did last time. There's quite a lot of material to cover on the thermodynamics and the behaviour of aerosol, and on cloud activation and cloud droplet formation in today's lecture. So what I'm going to do is just start off with a couple of slides that you'll have already picked up on. Could you remember where we got up to last time? Did we cover that slide? So we covered this, didn't we? We did the coagulation, sorts of calculations and what it does to the size distribution. We talked a little bit about condensation and what condensation does to a size distribution. We talked about chemical aging, how that can change the hygroscopicity of a population. And we talked about the sorts of reactions that can go on in cloud droplets. These were just examples. We'll go on to do more details on clouds later on today. And this was just an illustration of the processes that happen in clouds. So just to recap, interaction with water can largely be explained for aerosol particles by this diagram, where the relative volume, so this is the growth factor of a particle, will stay relatively low until the point at which soluble components can deliquesce. After that, particles can become bigger by taking on more water. As relative humidity decreases, you don't crystallise out the components until a much lower relative humidity. So what's the reason? Why don't you crystallise out things at the deliquescence relative humidity? Does anyone know? Well, the reason is that efflorescence or crystallization is a nucleation phenomenon. So it's a first order phase transition from the liquid phase to the solid phase, and it can occur at a range of relative humidities. And so this heterogeneous nucleation, why is it called heterogeneous? Do you know? It's because of the nucleation on any impurities in the droplets. That will happen at humidities depending upon how many impurities there are in the sample. The fewer impurities there are, the lower the relative humidity until you crystallise. The deliquescence point, if you look on a free energy diagram as a function of relative humidity, are you all familiar with the concept of free energy? Free energy in a purely chemical system is determined by the chemical potentials in the system. If you don't understand the chemical potentials and free energy, then go back and revise your chemistry. If not, I can go through some details, but these will come up in the problems a bit later on, and I'll approach this a bit more rigorously later on. But generally, the free energy of the system, varying as a function of relative humidity, says at the deliquescence point, you can move from a solid to a liquid. But as you reduce the relative humidity, you can go beyond the free energy equilibrium position until you crystallise out, depending upon how many impurities there are in the sample. So, I don't want to install anything. What's happening here? Cancel. Help. 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 Still spinning around, doesn't matter. So what do organic components do in a mixed particle? Do organic components crystallise out? Well, generally, organics hold on to water to much lower relative humidities. So they can push. This is not good. Something's happened here. Right, looks as though it's stuck. Bear with me a second, Warren. It is, and I've got a presentation slide up, and Windows wants to install something, and I've got a spinning wheel, and everything's frozen. That's very much it is. So, organic components can be found in most atmospheric particles, so they're not just inorganic components, and they will affect the crystallization behavior. So you won't deliquesce or effloresce particles at exactly the deliquescence point or the efflorescence point of the pure inorganic components. And as it says, recent field evidence shows organics and sulfates in mixed organic aerosols. And in some cases it says over 50% of the aerosol is organic. Actually, in some cases, 90% or more than 90% of the aerosol components are organic. And I can't show you any more slides. So, has anybody else downloaded the presentation? I'm just wondering, because I can I possibly get it up on my computer. Right, it's all right, I might have, okay, it's got a spinning, it had a spinning wheel on
right,
there.
it stopped.
No, I've just done it on my laptop instead.
Sensible, but I'll look at that when you finish.
Right, okay, because, so what it is, I had this slide, let me just check that this is the laptop. Yeah, it is, this is the laptop. Right, so it was on this slide, but basically it came up with install Windows. And I clicked the cancel, carried on spinning and everything locked out, so I couldn't.
And that's just using PowerPoint?
That's just PowerPoint.
There is no
Nothing else.
kind of files and
No embedded graphics.
How strange. I'll certainly... How long are you in for?
I'm in for 2 hours, so I'll finish in here at 4.
I'll check later. Oh, sorry
All
about
right,
that.
no problem. All right, it's all right, I got it on. Thank you. Right, okay, so where were we? Right, okay. So the effect on the deliquescence and efflorescence behaviour of organics can be seen. This is going to be really awkward. Okay, you can see here that you get you hold on to the water for much longer as you are drying out the particle when you've got organics. And you can hold on to the, oh dear, it's very difficult. Okay, so you can hold on to the water in the metastable region when you're drying out particles, but also you can increase when you're deliquescing, whether you can increase the water content below the deliquescence point. So multi-component particles don't just follow this clear deliquescence efflorescence behaviour. Now, I have no idea whether this will work. Oh, it does. So you can see deliquescence efflorescence from the transition. I'll stop it when it gets up to. So you can see if you step through for pure sodium chloride particles, and I'll turn off the sounds, you can see that at the transition point from about 74% relative humidity here to 75% relative humidity here, you've got a very abrupt transition in these particles. So these are sodium chloride particles which show a very, very abrupt transition. So there's no contamination in these particles. However, when you have not just mixed organic inorganics, if you have mixtures of inorganic components, then they can exhibit behaviour that's not just a clear, abrupt deliquescence and efflorescence. So normally what you'd expect is at the increasing relative humidity, you get an abrupt transition. You go beyond that abrupt transition as you dry out to hold on to water at lower relative humidities. But if you're in mixed components, here we're talking about an ammonium sulfate, ammonium nitrate mixed particle. So here, the ammonia fraction is shown on this axis, the sulfate fraction is shown on this axis, and this is a particle at relative humidity of 98%. So if you see this particle just here, when you decrease the relative humidity, it shrinks and loses water. At this point, it hits the surface where ammonium sulfate is precipitated out. At this point, it hits a phase boundary where litovicite, which is a mixed salt, precipitates out. And then finally, you get completely crystallized particles, which are mixtures of litovicites, 2 ammonium nitrate, ammonium sulfate, or 3 ammonium nitrate, ammonium sulfate. So what happens is you get multiple stages of the crystallization of the individual components. So you don't have just liquid or solid. You get a mixture of liquid and solid in equilibrium with multiple solid phases as you effloresce. So multi-component particles will exhibit complex phase behaviour. So if you watch again, the particle shrinks, first of all, loses water, and still remains this mixture of an aqueous ammonium sulfate, ammonium nitrate particle. Then you first start precipitating out some ammonium sulfate, so it becomes a bit solid. Then you precipitate out some litovicite, so that's one-to-one mixture. I've just turned the sound off. Why is it making sounds? And then, as it fully goes down the final phase boundary, it's a mixture of these mixed salts. So what we'll do is we'll just go on to some simple fundamental thermodynamic calculations for the sorts of things that lead to the partitioning between gas phase and liquid phase and solid phase components. It's very complicated thermodynamically to deal with very complex mixtures. So we'll just illustrate some of the tools that we'll use in dry gas-solid equilibria, and then some, I think we just do gas-liquid equilibria. I'm not sure whether we do gas-solid and liquid equilibria, but we'll move through these. But what happens? Does anyone know what the equilibrium point is in a multi-phase mixture? What defines the equilibrium point? Energetically and thermodynamically, what's the equilibrium point? Well, it's where there's a minimum in the free energy. So the rate of change of free energy from one phase to the next phase is 0. So dg by dn, so dg by dn equals 0. Now, if you're just in a chemical system and you've got no contribution from the pressure, temperature, the kinetics of the system, you're just talking about the chemical potential of the system, then this means that the rate of change of chemical potential is 0 at equilibrium. So if you've got ammonia plus nitric acid going to ammonium nitrate, this is just in the solid phase, or you've got ammonia plus sulfuric acid, so that's 2 ammonia plus sulfuric acid going to ammonium sulfate, solid ammonium sulfate. The equilibrium free energy expressions are the chemical potential on the left equals the chemical potential on the right. So the chemical potential in the first case of ammonia plus nitric acid equals the chemical potential of ammonium nitrate. So you take that to the left-hand side, and the sum, the total net sum of the chemical potential is 0. So that gives you the condition that the Gibbs free energy change at equilibrium equals 0. And the same for ammonia, sulfuric acid and ammonium sulfate. So twice the chemical potential of an ammonia molecule plus the chemical potential of a sulfuric acid molecule minus this chemical potential, which is taken over to the left-hand side of the ammonium sulfate, equals 0 at equilibrium. And that allows us to evaluate what the equilibrium values are. So for an ideal gas, we've got the chemical potential as a function of temperature and pressure equals the standard potential plus RT log of the vapour pressure. And for a solid, the chemical potential is just the standard potential at that temperature and pressure. So what you can do is put these back into this expression here and exponentiate to come up with this expression. So where the Pi here is the P of ammonia or, times and the P of nitric acid. So this is the pressure of ammonia and pressure of nitric acid expressed in terms of the standard potential of ammonium nitrate, the standard potential of ammonia and the standard potential of nitric acid. And that is a constant. Because that constant has the units of P squared, it's the partial pressure product of the system. So the equilibrium constant that defines how much gas and how much solid you have at equilibrium in the ammonium nitrate system is the partial pressure product of the system. And here, this partial pressure product is actually expressed in parts per billion. Because you can do that just experimentally. It's empirically determined. So what we have here is this partial pressure product has been measured in the lab. And the log of the partial pressure product is given by this expression. And also in the lab, you can measure the deliquescence relative humidity. So what's the deliquescence relative humidity? What's it defined as? Well, it's the point at which you start taking water on. So if you look at this expression here, these two expressions apply when there's no water. Okay? And so this expression for ammonium nitrate only applies when there is no water. And this is the condition that says below this deliquescence relative humidity, you have no water, and above this deliquescence humidity, you have water. So below this value here, then your equilibrium relationship will apply. So can anyone do this calculation for deliquescence relative humidity? And you put in 308 Kelvin. So at 308 Kelvin, what is the deliquescence relative humidity? Anyone come up with an answer? Okay. So what does that say? That deliquescence relative humidity is 57.1 degrees, percent. Okay? So 57.1%. What does the question say? 308K and 30%. So does the equilibrium relationship apply? Yes, because there'll be no water. Okay? So if that said at 60% relative humidity, you couldn't use the expression. Because it says it's 308K and it's 30% humidity, then it says that you can use the expression. So the only way of knowing whether or not you can use the equilibrium expression is to know whether or not you are going to have water involved. Because it's 30% relative humidity, you won't have water involved, so therefore you can do the calculation. Right. So what is the calculation asking us? It's asking us to calculate the mass of ammonium nitrate if you've got 17 micrograms per cubic metre of ammonia and 63 micrograms per cubic metre of nitric acid. So would you have ammonium nitrate in that system? Do you know? So what is the... How many parts per billion is 17 micrograms per cubic metre of ammonia? What's the molar mass of ammonia? $17. Okay, so if you've got 17 microgram per cubic metre and it's got a molar mass of 17, then it's 1 micromole per cubic metre. Okay? How many moles of ammonia of nitric acid do you have? One micromole, because it's 63. Yep, and you've got 1 microgram per cubic, 63 microgram per cubic metre. The molar mass is 63 gram per mole, so you've got 1 micromole. Okay, so you've got 1 micromole of ammonia per cubic metre, you've got 1 micromole of nitric acid per cubic metre. How many or what's the mass of 1 mole? Sorry, what's the volume of 1 mole? $22.4 times 308 divided by 273. Okay? Just by the ideal gas law or Boyle's law, and you can calculate the volume. So you know what the volume is of 1 mole. You've got 1 micromole of each per cubic metre. So you know how many metres cubed there are. You know how many meters cubed are occupied by 1 mole. You know what 1 micromole is. So you can calculate what the pressure or the partial pressure is in parts per billion. Okay? And it turns out that you've got 25 parts per billion of each. So, shall I do the... So that's the volume of 1 mole. Yep. You have 1 micromole. So this is, so it's times 10 to the minus 3 meters. Okay? Cubed. 10 to minus 6, isn't it? 3 or 6. How many litres cubed are there? There's a litre, yeah. 22.4, so it's 1,000th, yeah. So it's this number of cubic meters. You've got 1 micromole per cubic meter of ammonia and of nitric acid. So this is the number of micromoles per cubic meter divided by the number of cubic meters gives you the number of parts per billion. It's about 25 times 10 to the minus 9. So 1 times 10 to the minus 6 moles. Can anyone do this calculation? 22, well, it's roughly 22 times 10 to the minus 3 divided 10 to the minus 6. 6.8 times, so 6.8, sorry, how is that 6.8? Times 308 divided by 273. Zero 0.02 meters cubed. Yep. And there's 1 micromole per meter cubed. So 0.02 times 1 times 10 to the minus 6 moles. Yep. Each occupying 1 micromole. 1 mole occupies this. 1 micromole occupies, is it 0.02 or 0.025? Yeah, okay, that's about right, yeah. Okay, good. So it does come out to 25 times 10 to the minus 9. Right, so I was panicking then, I thought I was missing that last point, 0.05. Okay, so that tells you how many parts per billion. If you've got 25 times 10 to the minus 9, how many parts per billion is that? Okay? 25 parts per billion. So what's the partial pressure product? There's 1 micromole of ammonia, which is 25 parts per billion of ammonia, and 1 micromole of nitric acid, which is 25. So 625. So P NH3 times P HNO3 equals 625 parts per billion squared. It's actually 639 because you missed off the point. Yeah? So really that's 639, but let's call it 625. So, if you've got 625 parts per billion squared, what is the value of the partial pressure product at 308K? Can somebody do the calculation? Okay. So that's the partial pressure product at 308K. This is how much ammonia you have. Ammonia and nitric acid you have, 639. So what does that tell you? Too much gas. So you're supersaturated. Okay, you're more than the saturation level of gas. So you will form nitric acid. Because, ammonium nitrate. Because you've got nitric acid and ammonia in excess of the partial pressure product, you're supersaturated and you will form some ammonium nitrate. How much ammonium nitrate will you form? How do you calculate that? So say you've got about 25 parts per billion of ammonia, haven't you? And you've got roughly 25 parts per billion of nitric acid. You've got it in parts per billion. How do you measure parts per billion of ammonium nitrate? Unfortunately, it's a solid, so you've got a phase transition. So you can't go from volume of a gas to volume of a solid. So it's no longer a part per billion because you condensed it. So you need to have it in mass. So imagine X condenses. You've got 25 in the gas phase. 25 minus X condenses. So therefore, 25 minus X squared equals your partial pressure product, which is 318. Is that how you did the calculation? Right. So you go from there. How do you get? So, what do you go? 7? you said 8. I think it's, my calculation was 7.18. Maybe it's 8. Whatever the calculation is. But that's how you calculate how much has turned into ammonium nitrate. So 8 parts per billion, roughly, of gas has been turned into nitric acid. So what's the molar mass of each? Well, 17 for ammonia and 63 for nitric acid. Okay? So, well, you've got 7 parts per billion, or 8 parts per billion of ammonia at a molar mass of 17, which do the reverse calculation. It comes up to be about 4.18 microgram per cube. Is that right? 4.82 and 17.87. So this is how many micrograms per cubic metre 8 parts per billion is of each gas. 8 parts per billion of ammonia is 4.82 microgram per cubic metre because it has a molar mass of 17. 8 parts per billion of nitric acid is 17.87 microgram per cubic metre because it has a molar mass of 63. So you've got about 22 microgram per cubic metre of ammonium nitrate. So this is saying if you have 25 parts per billion of ammonia, 25 parts per billion of nitric acid, you're supersaturated, and so you form 22 microgram per cubic metre of ammonium nitrate. So the steps that you take, first of all, to establish that you're at the equilibrium position, you know the deliquescence relative humidity. Calculate the partial pressure products. Calculate the mixing ratio of each of the components. The partial pressure product is the mixing ratio minus the amount that's condensed squared. Then you calculate the amount that is condensed. Just for the quadrant. That allows you to calculate how much mass for a given gas loading. So there's another example of this here. I'm not going to work through this. You're going to work through this, and then you're going to ask me questions after Easter if you don't get it still. Because these are the sorts of calculations you need to do to be in order to be able to calculate how much aerosol loading for a given gas phase. So the answer is there, but it's just following the same sort of procedure. Okay? So go through that in your own time. I'm not going to go through it. You do that and then ask me any questions. Tells you each of the steps. So, by the time you've gone through those examples, you'll be expert at the sort of questions that you need to understand the partitioning of solid particles and gas phase components. So now what we're going to do is talk about the gas aqueous equilibrium. So if you remember condensation, you can condense the gases to solids, or you can condense the gases to liquids. Now, Do you understand the term Henry's law solubility? Have you come across solubility? So the amount of material, so the concentration of material in the gas phase divided by the partial pressure gives you the solubility. So this tells you if you've got more gas, then the concentration divided by, the higher the gas phase concentration, the more you will have in solution. So your partial pressure product times your equilibrium constant, your partial pressure times your equilibrium constant will tell you how much you have in the condensed phase. So if you have 10 parts per billion, then you will have a stronger solution in your aerosol particles than if you had 5 parts per billion. So it just makes sense. If you increase the amount in the gas and it still has the same solubility, then you increase the amount in the liquid phase. So it's just a very, very simple relationship that defines the Henry's law solubility, just defines how much you have in an aqueous solution divided by, for every amount of gas that you have in the gas phase. Now what happens if you dissociate something? So if you have, now I do apologise to those of you that would like me to make everything clear on here, because the pen really isn't very good for the board. So I've actually checked. Has anyone ever checked on the podcast to see if you can read what's on the board? I checked, and when the pen's good you can, and when the pen's bad you can't. So you have to take these notes yourself. So if you have a component AC with a given concentration in the gas phase, and it dissociates to A minus plus C plus, then your solubility constant is defined by what you have in the condensed phase divided by your partial pressure in the gas phase. So your KH is just what you've got now. That is if AC, when it dissolves, instantly dissociates into both A ions plus C. So if you've got ammonium sulfate, so if this is it dissociates into directly into NH4 plus and SO4 2 minus. But if you have something that weakly dissociates, it doesn't fully go all the way across. So the example I've given there, actually it's gone to the next page for the example, but you can see here that you have AC dissolves but doesn't dissociate, so you've got some AC still in the liquid phase and some A minus and some C plus. And examples I've given here are carbonic acid. And does anyone know what this is? Acetic acid, so ethanoic acid. Okay? So let's look at the example for carbonic acid. You've got there the equilibrium relationships. So carbon dioxide dissolves in water and forms a complex. And that is in equilibrium with aqueous carbonic acid. The carbonic acid dissociates to bicarbonate plus hydrogen ions, so H3O+. The bicarbonate dissociates to carbonate plus more acidity, so more protons. So what is the solubility of carbon dioxide in water? Well, the solubility of carbon dioxide in the water is the sum of this aqueous component plus this aqueous component plus this aqueous component divided by the partial pressure of CO2. So what we've got is this first solubility to produce your carbonic acid is aqueous carbonic acid divided by the partial pressure of CO2. The second dissociation is the product of these two divided by the carbonic acid. The third dissociation constant is the product of these two divided by the bicarbonate ion. And you can calculate, and you can derive these concentrations from experiments. So what we want to do is derive what the true solubility of carbon dioxide is in water. So we have here H2CO3 from the first equation is the solubility, the true solubility of CO2 times the partial pressure, just from the Henry's law equation. The bicarbonate is simply K2 times the carbonic acid in solution divided by the acidity, and you can back substitute for the carbonic acid in solution from equation 1. And CO2 minus concentration is just given by the back substitution of the third expression. So as I said, that the total dissolved carbon dioxide is the sum of each of the individual components. So again, by the back substitution, you can come up with this expression. So what you're doing is you're just summing each of this expression plus this plus this. And taking this outside the brackets, you can come up with this expression. And you see that it's pH dependent. So it's saying that the solubility of carbon dioxide is pH dependent. So what's the Henry's law defined as? Well, the Henry's law is defined as what's in solution divided by the partial pressure. So what's in solution, that's this bit here, so that's this bit here, divided by the partial pressure is this. So it's just this divided by partial pressure is this, and that gives you the effective Henry's law solubility. So the true solubility is just this, okay? So it's the true solubility is this divided by partial pressure, whereas really you need to take into account the other components. So it's not just this, but it's this component and this component as well, and divide that by the partial pressure to get the effective Henry's law coefficient. So that tells you that the Henry's law coefficient for carbon dioxide is dependent upon the acidity. So what does that tell you about ocean acidification, for example? So if the oceans become more acid, the H plus concentration increases, so the solubility goes down. So it means that carbon dioxide cannot dissolve as effectively in the oceans as it can when they become more acidic, as it can when it's more basic. But that's the same in aerosol particles. So again, here's another exercise, because carbon dioxide is probably not as important in the atmosphere as it is to something like oceans. But N2O5 is important in the atmosphere because it's formed from NOx. Here are the equilibrium relations for N2O5 dissolution and hydrolysis and dissociation. So again, I don't want to go through this exercise. This is an exercise for you to go through in the same way as I did for carbon dioxide, just to have some practice. So again, in a couple of weeks' time, we'll go through this if you have any questions. So it's exactly the same steps. You've got dissolution, first of all, then you've got the hydrolysis in this case, and then you've got dissociation. And the answer's worked, again, and it just tells you what the answer is there. But just follow through all of the steps. Again, this tells you that the total dissolved NOY is dependent upon the acidity. So it says that N2O5 doesn't dissolve as well in acidic solutions as it does in non-acidic solutions. So what's the impact of that? What happens if you don't dissolve as much in acidic solutions? It means that you don't take up as much NOx to acidic particles as you would to non-acidic particles. So if your acidity goes up, then your N2O5 uptake on those particles will go down. Okay, so just go through that in your own time and tell me if you have any further questions. And there you go. Another exercise, just plugging those numbers into the equilibrium relations. And that just gives you some examples. So those, I've given you that presentation. You had that to take away a couple of weeks ago. So work through those examples again, if you haven't already. But just go through them so that you can ask me some questions in a couple of weeks' time. What I want to do now is go on to, hopefully, I hope this is the same as the one that I've put on Blackboard. Right. If I get to any strange slides, then we're going to have to go back to the Blackboard presentation, but I can't get that at the moment. But what I want to do is finish off these gas equilibrium discussions and move on to clouds. So the impact of particles on clouds for the rest of the lecture. I may need to finish off after after Easter on this. But this is just a summary of the expressions that were in the last discussion, the last example of carbon dioxide solubility. And all of these can be derived from those equilibrium expressions. And the one thing, where's my cursor? Right. The one thing to notice here is the relationships dependent upon acidity. So we know what the acidity is, we know what the, so you end up with a cubic expression in acidity there to calculate that from any given carbon dioxide concentration. The solution in terms of the solubility of carbon dioxide I've just plotted out here. So the solubility goes down as a function of the pH. So more acidity. No. What am I plotting here? The H plus concentration as a function Right, I'm going to skip over this, and I'm going to have to come back to you afterwards. What I was trying to do I was trying to be clever, and I plotted something last night that wasn't what I should have plotted. Okay. Right. So what we have here, this here is the, what I've called KH effective. So that's the effective Henry's law coefficient of CO2. And you can see here as a function of pH, the solubility of carbon dioxide goes up. And this says here what the micromolar concentration in solution of the carbon dioxide is. And this T, what do you think this T is? CO2T. It's the total dissolved carbon dioxide. So that's carbonate, bicarbonate, and carbonic acid. So it's the sum of all of those in solution. And you can see how much more you can hold in solution at the acidity that's close to the ocean acidity. So the ocean is around, well, somewhere just above pH 7, somewhere just above neutral. It's buffered. Or it should be. If you actually take the total seawater, did you know that they had a standard seawater? You can make up standard seawater. They have a recipe for standard seawater. If you make that recipe up, it comes out to just above 7 pH. And that can hold a significant amount of carbon dioxide. As you become more acidic, it can hold much, much less. So that's really just the solution to the expressions there, and that tells you how it's determined. But you can do the same thing for NOx and N2O5. In reality, though, we've already seen that aerosol particles are very much more complex than that. So they don't deliquesce and effloresce in the same way as individual components, because they have organic components and they have mixtures of salts. And so it's very, very hard to actually say what the atmosphere should do. You can say how the atmosphere will behave were things in the simple conditions that we're doing for these calculations. So what about ammonia-water equilibrium? So ammonia is the most dominant base in the atmosphere. It's the thing that neutralizes most acids. So ammonia plus water complexes, first of all, and then it dissociates to form NH4 plus OH minus. The same example, following the same example as before, the true solubility is just the amount of the complex in solution divided by the partial pressure. The first dissociation, that's this one, says the products divided by the complex are the first dissociation constant. To get the total dissolved ammonia, you need to add this plus this plus this, and so you add these two. So this can be expressed as KH times P. The product of these can be expressed as Ka1 times this. You can back substitute from here and you can come up with this relationship for the total NH4 plus. So that tells you how much ammonium you've got as a function of the equilibrium constants, the gas phase ammonia, and the pH. So what does that tell you about ammonia solubility? Well, it tells you that you can dissolve more when you're acidic. So unlike CO2, ammonia becomes more soluble when you're in acid. So you can see that the total amount of dissolved ammonia is just this plus this, which equals this expression in terms of the two equilibrium constants, but importantly noting that the H plus concentration is on the top here instead of on the bottom. So the total ammonia goes up as you've got more acidity. So the amount of ammonium, free ammonium in solution, divided by the total ammonium in solution. So the total ammonium is the sum of these two. The free ammonium is given by this expression here, just from this divided by this. And you can see the relationship between pH and the aqueous fraction of ammonia. So the aqueous fraction of ammonia is NH4 total as a function of the NH4 total plus the PNH3. And you can see the aqueous fraction goes up as the pH goes down. Now, what do these three lines represent? Does anyone have any idea? These three lines represent how much water there is. If you increase the amount of water, then for a given amount of dissolved ammonia, for a given pH, you get an increase in the amount of dissolved ammonia. because you're more dilute solution. And this is a concentration. To maintain the concentration with increased water, you have to have more total dissolved. So this says that if you have more water, you can dissolve more ammonia because it's more dilute solution, and you can maintain the pH higher because you've got more dissolved ammonia. Sorry, where is water here? Well, what is this? What's the units of this? This is concentration. Yep. So it's concentration in solution. So it's amount of ammonium total divided by the amount of water. Yeah. So the liquid water implicitly is in the concentration of all of the Henry's law coefficients. Okay? Because it's per unit amount of water. So what happens when you go away to the lab and you measure all of these solubilities of all of the gases? Well, you find that you can have a very, very wide range of Henry's law solubilities. Now, I always choose these units because it makes most sense to me. So this unit here is molar. So that's moles per cubic meter, moles per litre, per atmosphere. And if you look at the Henry's law coefficient, it's the number of moles per litre divided by the partial pressure. So molar per atmosphere makes the most sense to me. And you can see the very, very wide range of solubility. From 10 to the minus 4 to 10 to the 14. So that's 18 orders of magnitude solubility difference between C10H22. So what's C10H22? Alkane. It's decane. Yep. C10H22 is decane. So its solubility, because it's very, very non-polar, says that you can only get up to 1/10,000th of a mole per litre for one whole atmosphere of pressure. So if the whole atmosphere was made of decane, you could only make a solution that was 1 part in 10,000 because it's very, very insoluble. And you can go right to the other end and find the solubility of HBr, so that's hydrobromic acid, at pH 8, or is that pH 6? It's very blurred. But anyway, you're talking about 10 to the 15 molar. So you'd have 10 to the 15 moles per litre. Is it possible to have 10 to the 15 moles per litre? No. But is it possible to have one whole atmosphere pressure of HBr? Basically what it's saying is that at the atmospheric parts per trillion level of HBr, you would have a very strong solution of hundreds of moles per litre. But you can have a range of 18 orders of magnitude here between things that have been measured in the atmosphere and their solubility. And this was a paper by a colleague of mine, Rolf Sander, in Surveys in Geophysics. So what is the pH of aerosol? Now, we've already seen on one of the earlier plots that it's very dependent upon liquid water content, because what's the formula for a pH? Okay, so it's minus the logarithm of the hydrogen ion concentration. Hydrogen ion concentration has units of moles per litre. That's water. If you have more water, then the hydrogen ion concentration decreases. So your pH will go up if you have a more dilute solution. So these are standardised. These are pHs measured under standard dilution conditions. But you can see here that the pH range across the US has gone from quite, well, not quite neutral, so it's acidic at around pH 5, down to pHs of less than about 4.3. So it's not a very large range, but don't forget it is a logarithmic range. So you're talking about an order of magnitude in hydrogen ion concentration. And on the east coast, you're more acidic than you are on the west coast. Do you know what the situation is like in China? Any idea what the pH is like? Sorry? Depends where you are. Where do you have lots of ammonia? Okay. In a lot of agricultural regions in China, you're actually nearly neutral. Okay, because you've got lots and lots of ammonia. In other areas, you are going down to about 4, 4.5. Just depends upon the amount of neutralising bases that are around. So, as I mentioned, all of this depends upon the liquid water content, the amount of liquid water that there is in the atmosphere. So we're going to kind of switch gear now to increase the amount of liquid water in the atmosphere. Are you familiar with the saturation vapor pressure curve of water? If not, get familiar with it. It's in your interests to be familiar with the saturation curve of water. Okay? So what does the saturation curve tell you? Well, it tells you that if you have too much water vapour, then it cannot stay as vapour in the atmosphere. That's all it tells you. And this curve tells you how much water you can have as a function of temperature. So can you, if you've got a relative humidity of 20% in the Arctic and 20% on the equator, which has the highest amount of water vapour? The temperature just goes up along here, and you can see that as a function of what's happening here. That as you increase the temperature, the saturation, the amount of water that you can hold at 100% relative humidity increases as a function of temperature. So 20% of this line, somewhere down here, at the equator, at this temperature, is higher than 20% in the Arctic here. So this line is the 100% line. This is the limiting line for how much you can hold at equilibrium in the atmosphere. And that's the saturation vapor pressure. But there are two saturation vapor pressures. Because water can be in 3 phases in the atmosphere. There aren't very many compounds that can be in 3 phases in the atmosphere. Water's one of them. Not the only one, but it is the most dominant one by a long way. Now, the saturation vapor pressure over water is greater than the saturation vapour pressure over ice. So you can't hold as much ice in the atmosphere at a given temperature as you can hold water. Now, any parcel of air to the right of this curve, so if you've got an air parcel with a temperature here and an amount of water here, it's unsaturated. So it's got a relative humidity less than 100%. If you've got an air parcel between X, Y, and Z, it's unsaturated with respect to liquid water, but it's saturated with respect to ice. So that would mean that if you had a droplet, a water droplet, and an ice droplet, an ice crystal, and it was in a condition between X, Y, and Z, then you're unsaturated with respect to the liquid water droplet, so the liquid water droplet will shrink. But you're saturated, you're in saturated conditions with respect to the ice, so you'd have to move to form the condensed phase. So your liquid water drop would evaporate and your ice crystal would grow. So that's unsaturated over here. It's conditionally saturated here, so it's unsaturated with respect to water, saturated with respect to ice, and above here, it's fully saturated. So how do you get saturated? So if you've got an air parcel over here, how do you become saturated? So, if you remove sensible heat, so you decrease the temperature, remove sensible heat from the air parcel from here, you reach this point. And that's called the dew point temperature. Are you all familiar with the dew point temperature? Okay, that's good. So what's the other way of doing it? Okay? So you increase the amount of absolute humidity until you get to a relative humidity of 1. Okay? That reaches 100% humidity. So what's the other way? So what you've got there, decrease temperature or increase the humidity. We've got everything in between, haven't you? So this goes horizontally, this goes vertically. What is the quickest way to get from here to here? Or the shortest distance? How do you do that? Sorry? You adiabatically evaporate water. Yep, so the adiabatic evaporation of water moves you at dq equals 0, so constant Q, using the latent heat of the sample. And that, the adiabatic saturation temperature, is the thermodynamic wet bulb temperature. Are you familiar with wet bulb measurements? Dry bulb and wet bulb measurements. So if you adiabatically evaporate the water, you get to the adiabatic saturation temperature. So just to recap, remove sensible heat, you go horizontally. Add water vapour, you go vertically. Move perpendicularly, and you adiabatically evaporate water. Okay. So what do you do in a fog or a cloud then? Which do you do it? remove sensible heat? Do you add water vapour, or do you adiabatically move? You kind of pseudo-adiabatically. You kind of try to move adiabatically, but sometimes you're not quite following adiabatic lifting. So there are a number of mechanisms that you can get to saturation. So there's if you can radiatively lose heat, causing cooling, you can get to a radiation fog. So when you reach the dew point temperature, that's just cooling horizontally. That's how you get to a radiation fog. Now what happens as you thicken, the top of the layer acts as the cooling source for the layers above, and you get deeper and deeper and deeper fogs. And these can persist, and these can go on for ages, long time in winter time particularly. Advection fog, moist air advective over a cooler surface. So what are you doing there? How are you reaching saturation with the moist air advected over a cooler surface? Is it adiabatic? Is it just cooling? Or is it adding moisture? It's kind of, well, you're kind of moving the moisture, so and then you're over somewhere that's removing the temperature. So it's almost, it's like removal of sensible heat. And then cloud formation is normally imparting a cooling by lifting in the atmosphere. So how do you lift? Convection, large-scale lifting, orographic lifting, or mixing of air of different temperatures and vapour pressure. How does the last one give you a saturated air parcel? If you mix air of different pressure and different temperature and vapour pressure, how do you get a cloud forming? Yep, simple, it's just the curvature. So the curvature of the lines, so if you are here, you've got an air parcel here, and you've got an air parcel here, 50% of each, you hit the saturation line when you mix them. So you mix 50% of air from here, 50% of air from here, you get over here. So mixing of air parcels, so you get convective lifting, large-scale lifting, force lifting from orographic, and then mixing of air. So you're familiar with all of the different cloud types? Yeah? Not really. Well, how many of those have you seen? How many of those different types of clouds have you seen? How many have you not seen? Has anyone not seen any of those? I guess you've all flown Have you all flown circles over the north? Actually, all of them, yeah. Okay, so none of those you're unfamiliar with. So you can say how will you reach saturation to get to a nimbostratus? How would you get to saturation in an altostratus? How would a swelling cumulus have got to supersaturation? Would it be fair of me to ask those sorts of questions in an exam? I'll leave that to your imagination. So the rest of this lecture, I think I'm just going to talk about couple of problems in cloud formation. And these are all going to relate to how water interacts with a curved surface. So, are you familiar with the term water activity? Does anyone understand what water activity is? So if you had let's take this one. So if you've got an ammonium sulfate particle in the atmosphere at RH of 90%, and you've got your ammonium sulfate particle, how much water should I draw around this ammonium sulfate particle? Would it be this big? Would it be this big? Or would it be it'd probably be about 9 times the mole fraction, not the volume. Okay? So X of water, so that's the mole fraction of water, would be 0.9. Okay? X is the mole fraction. So X of NH4 to SO4 is 0.9. But what's that really? Really, just from this is just as a bit of a X of NH4 plus equals 1.8 and X of SO4 2 minus equals 0.9. Yep. Because it dissociates. So mole fractions the mole fraction of the electrolyte, or the solubilized material, and the mole fraction of the water must equal 1. I'm going to get rid of this because this is not strictly correct. But anyway, the mole fraction of the dissolved material plus the mole fraction of... Am I being stupid? Must equal 1. Now, in reality, it will be slightly it'll probably be about 0.89. And this would be, in reality, about 0.11. Do you know why? No, that's without any curvature. So imagine that this was just in a beaker and it was a bulk solution. In reality, you wouldn't be 0.9 and 0.1 at 90% relative humidity. In reality, there are interactions between the molecules that mean that the mole fractions aren't always completely the same as the saturation ratio. And this is called non-ideality. So the mole fraction of water will be 0.89, but the activity of water still equals 0.9, and the activity of ammonium sulfate still equals 0.1. So at 90% relative humidity, the activity equals 0.9 if it's 90% relative humidity. The mole fraction will be close to 0.9. As you get to 70% relative humidity, 60% relative humidity, the deviation between the mole fraction and the activity becomes greater. What relative humidity do we have in clouds? Almost exactly 100%. What is the activity of water? It's not 100. It's not 1 because of the curvature. Okay? It's kept below 1. It's impossible to have an activity greater than 1 because you cannot have more material than you have water. Okay? So, what happens? The activity is the relative humidity, which is just the pressure of water divided by the saturation vapor pressure of water. Over a curved surface, the surface tension reduces the water activity. So the activity of water is the relative humidity divided by the Kelvin term. And the Kelvin term has the radius of a particle, something called the partial molecular volume, so that's the molar mass divided by the density, the surface tension, and RT. So it says that the smaller the particle, the higher the curvature, and the higher the Kelvin term. So the smaller the particle, the higher the Kelvin term, and the lower the water activity. So the water activity is no longer the relative humidity. So the saturation ratio, which is the relative humidity divided by 100, is the water activity times the Kelvin term. Have you seen these Kohler curves before? Have you all seen Kohler curves? The Kohler curve is the sum, or the product, complicated, is the manifestation of both of these terms acting in competition with each other. So you can see that as the supersaturation, so this is 100.1%, 100.2%, 100.3%, as the supersaturation increases, a particle of this diameter will increase in size as the supersaturation increases until it reaches a peak, and then at this point it will just grow and grow and grow and grow and grow without any more increase in supersaturation. Because of this relationship between the activity of water, the relative humidity, and the Kelvin term. Because at this point, the activity of water will have got so high, because you've got this increase in supersaturation, that no longer your radius of your drop has got so big that you no longer need that same amount of activity in order to keep growing. And so you've got over this hump. You're over the limitation of the curvature. So what you can, you don't really need this. This is kind of background reading. But basically, it's because as you bend a surface, the molecules can escape. So if the molecules can escape, what's that do to the vapour pressure? It increases the vapour pressure for the same amount of water. So it would mean the vapour pressure over a curved particle is higher than over a flat surface. As you curve it more and more and more, the vapour pressure gets higher and higher and higher. So you need more and more relative humidity to keep the particle growing. Because your molecules are wanting to escape, you're wanting to grow it, etc. So it's harder to grow a small particle than it is to grow a large particle. So here is a schematic diagram of the Kohler curve, where this is the Kelvin term, which decreases as the drop radius increases. Here's the solute term. So this is represented by the activity. The activity increases as this activity of water increases as the supersaturation increases. And overall, the net sum of these two curves gives you the red curve. And this point here, if you increase above this value of critical supersaturation, it means your particle has grown above this critical radius, and it says you will now be a cloud drop, and you'll just grow. So if you lift an air parcel with droplets in that are of a given size, and they take on water enough, because the supersaturation is high enough to reach this point, they will then become droplets and stay in the cloud. If you only lift them to this point, when you reduce the supersaturation, they shrink again. If you lift them to this point, they grow up here, and you can afford to reduce the supersaturation from here right the way down to here before they'll start shrinking again. So the left-hand side, the rising branch of humidity is stable because you're increasing the supersaturation, you're increasing the size. You decrease the supersaturation, you decrease the size. It's stable. For any given humidity, you know what size it is. When you get to the critical point, you grow and you run away because you can decrease the supersaturation, but you'll still keep on growing. And you can have multiple curves. So if you have a particle that's got a diameter of 50 nanometers, it needs more critical supersaturation than a particle of 100 nanometers in order to become a cloud droplet. Because of the Kelvin term, because there's less resistance to growth of a larger particle because it's not as curved, it doesn't need as much supersaturation to become a cloud droplet. And if you go up to a 500 nanometer particle, almost any supersaturation at all will turn it into a cloud droplet. Sodium chloride and ammonium sulfate have different affinities for water, like we saw earlier. So they have different Kohler curves as well. So you see from this expression, I've gone back a slide here, this is the true expression for the Kohler equation. But you can make an approximation to the Kohler equation such that the saturation ratio is given by A over R minus B over R cubed. So instead of having to evaluate an exponential, I could ask you in your exam to evaluate a sum. So I think it'd be much, much fairer for me to ask you to manipulate sums than exponentiate. And it also means that some problems are soluble when you make an approximation than when you try to explicitly solve. So you can approximate the Kohler curve to this expression. And A, do you know what these terms are here? Well, the Kelvin term is A over R, the solute term is minus B over R cubed, the total is this. A is, so can you remember what this expression, this term here is? Well, that's just the molar mass of water. That's the surface tension of water. That's RT, that's the density of water. That's the partial molar volume. That's the mass of the solute. How do you know what the mass of the solute is in a cloud droplet? What is the solute in a cloud droplet? The solute is the dissolved part of the particle. So if you know what the mass of the particle is, if it's completely soluble, that's the mass of the solute that goes into this term here. So the molar mass of water, molar mass of the solute, and the density of water. So all of these things are completely tractable. So we know what they are, so it's possible to work out what the Kelvin term is, to work out what the solute term is, and to work out what the critical supersaturation is. Because the critical radius and the critical supersaturation have these relationships. So, let me just see before I... Okay, right, I know what I'm doing. What I'm going to do, I know where I'm going to stop. Right, what we'll do, we'll run briefly through this exercise and I'll move on to the beginning of the next bit, and what we'll do is we will finish this work off. Here's how we'll do it. So, next week we'll do the last of the gas phase lectures. Then we have 2 more after Easter, don't we? If you want. You don't have to have them. But if you do want them, what I'll do is finish off this lecture and then use the rest of that lecture to go through all of your example problems in aerosol. And then the following one, I'll go through all of the example problems in your gas phase. So, I'll just take you through this exercise because this will be another example of the sorts of things that you'll get for clouds. If you've got a particle of dry radius, now you remember what I was just saying, that's going to be the thing that dissolves and acts as your cloud seed. If you've got a particle of dry radius 50 nanometers, and it's made of ammonium sulfate, so that's just soluble material, and it's large enough to activate in cloud formation, how do you calculate the critical supersaturation? So calculate what the supersaturation is in the cloud that's just large enough to activate in cloud formation. Well, you're given all of these terms, which are the terms that go into A and B. You know what the critical supersaturation expression is. You would be given this if it were an exam question. The solute mass is 4/3 pi times the density of ammonium sulfate times R cubed, so that's 50 nanometers cubed. That tells you it's 8.9 times 10 to the minus 19 kilograms. The NS, so sorry, this is here. Right, this is the number of this is the number of ions that ammonium sulfate dissociates into. So ammonium sulfate has got 2 ammonium and 1 sulfate. So you can evaluate A, you can evaluate B, and you can calculate the S. So this says that the critical supersaturation that you need is 1.4 times 10 to the minus 3. To activate a particle of 50 nanometers. So that 1.4 times 10 to the minus 3 is 0.14%. That is a 0.1 micron diameter, so that's a 50 nanometer radius, so 0.1 diameter, ammonium sulfate particle. So you can see there, this calculation is just calculating what this point is on the Kohler curve. So that says that at that point, at 1.4 times 10 to the minus 3 supersaturation, the particle has grown to be 495 nanometers in diameter. So this 100 micron diameter, 495 micron nanometers in radius. So this 100 nanometer diameter particle has grown to be 1 micron at the point at which it becomes a cloud droplet. So that's the sort of calculation you can do, and manipulation of the data. What I'm not going to do is go on to what happens inside cloud. So this talks about the activation. No, I won't need to do that. Okay. I'll go through that at the beginning of the lecture after Easter. But just go through the worked examples that you've got, and that will be enough for you to ask me questions with after Easter. So is everyone comfortable with going away and having a go at those worked examples and coming back and asking me questions later? Good? Thank you very much. Shall see you all later. Has everybody signed the sheet? Who has the sheets?